Hello and welcome to this video in which we compute the Fourier series of an arbitrary square wave. The square wave is arbitrary in the sense that the amplitude is some constant a and the period is some constant t, and the duty cycle, which is a number between 0 and 1, is some arbitrary value. So it's a symmetric square wave would have a duty cycle of 1/2. Okay, so the goal here is to finish this by having computed the Fourier series coefficients. So let's begin. First we have C0, which is the DC component. This is 1 over t, the integral from 0 to t of x of t dt. Okay, and if we work this out, between 0 and t, our signal x of t is equal to a. So we'll have a dt, and it's equal to a when t is between 0 and d times cap t. And so if I work this out, I get a times d. Okay, so this is the average value of this signal. Now, one thing I forgot to do, which I should have done immediately, is omega 0, that is our fundamental frequency of this periodic square wave, is 2 pi over its period, where its period is t. We'll need that in just a minute when we compute c sub k. Okay, so there's C0. Turns out that, again, this is the average value of the waveform averaged over one period. So let's see. Let's go ahead and do c sub k, where k is not equal to 0. So this is again going to be 1 over t, the integral from 0 to t, x of t. And now the thing that's different between this and C0 is e to the minus j k omega 0 t dt. Okay, so hopefully this makes sense. Again, this is just the definition, or I'm sorry, the formula for c sub k when k is not equal to 0. And now we have 1 over t. Again, x of t is a when t is between 0 and dt and 0 otherwise. So I can write this as the integral from 0 to dt of a e to the minus j k omega 0 t dt. Okay. And this then, let's see, if we work this integral, we'll have an a over t 1 over minus j k omega 0. That's basically this exponent up here. And then we'll have e to the minus j k omega 0 t evaluated between 0 and dt. Okay, so hopefully you're sticking with me. So far so good. So we still need to do some work on this guy though. Whoops, kind of made a mess of that. Let's actually grab this and copy it onto another workspace and keep going with it. Okay, so this is what we're working with then. We have that this then would be equal to a over t times minus j k omega 0, and then e to the minus j k omega 0 dt minus e to the minus j k omega 0 times 0. Okay, now we can start to simplify things. First off, we have e to the stuff times 0, so it's e to the 0. This guy just becomes 1 because e to the 0 is 1. We also, if you'll remember, we had that omega 0. This is 2 pi over t. So we have this t multiplied by all of this, which is 2 pi over t. Those two will cancel. And we have a similar thing up here. We had e to the jk omega 0 is 2 pi over t. So this t and this t will cancel. And so we also have a negative sign down here. So let's use this to write this as a j k 2 pi times 1 minus e to the minus j k 2 pi d. Okay, can we simplify this any further? And the answer to this is yes, but it's going to look a little weird to get to that point. Let's see. Well, so this really is a perfectly good stopping point, but it turns out that if you manipulate it a little further, you can actually get some insight into what this is going to look like. And so I'll go ahead and do that manipulation just to show you what this will look like. Besides, this sort of stuff is good for you. So let's see. Why don't we copy this to another workspace so we've got plenty of space to go in. And the next little bit is going to be one of those things where when you know what the answer is you're trying to get and the form is you're trying to get, it makes sense to do what I'm going to do. But the first time you see it, you're probably going to say, why on earth would you want to do stuff like that? So the first thing I'm going to do is I'm going to take this expression we have and I'm going to multiply it by 1. But I'm going to express 1 in a very complicated way. So I'll have e to the j pi k d times e to the minus j pi k d. Okay, so hopefully you can look at these and say, well, the exponent here is the negative of the exponent here, so this is indeed 1. But this is a very complicated way to express 1. So the next thing I'll do is we'll mess with this guy out here just a little bit. We'll write it as a over k pi, and then we'll write the rest as 1 over 2j. So I've taken this 2j and factored it out of the k pi. Now we'll take 1 and multiply it by this first term here. So we have e to the j k pi d. And then we'll take this term and multiply it by this first term. And so we have e to the minus jk 2 pi d, e to the jk pi d. This will end up being e to the minus j k pi d. And then we'll have this guy out in the end here, e to the minus j k pi d. Okay, so why did I do that? Well, it turns out almost magically, if you remember Euler's formula, this actually is the expression for the sine of k pi d. Isn't that cool? And the next thing I'm going to do is I'll multiply the top here by d and divide by d, so I haven't changed anything. But now I'm going to take this dividing by k pi d and put it under this sign. So I have k pi d, and I'm still left with the AD times this guy, and then e to the minus j k pi d. And this sine, k pi d over k pi d, shows up often enough it's got a name. We call this the sinc of k pi d. And the sinc function, if you haven't run into it already, it's high time you did. The sinc of its argument, so let's say sinc of x, as a function of x, looks something like this. So basically what I would do is for each value of k, I would take k times pi times d, plug it in here, and that would give me the particular value that I have here. You can think of this almost as being an envelope of the Fourier series coefficient. This is the magnitude of the Fourier series coefficient, and this guy here, the magnitude is 1, and this just is a phase change for the Fourier series coefficient. Okay, so the end result that we have is, this is AD sinc k pi d, and this is times e to the minus j k pi d. Okay, so again, this gives us our amplitude of our sinc function. This is the sinc function, which gives us the actual magnitude of the Fourier series coefficient, and this is a phase shift on those Fourier series coefficients. So hopefully you found this useful, and thanks for watching.